All right. So today is, what is the day? Today is Tuesday, September 22nd. We're in week 6. All right. We're going to finish 2.4 on complex numbers, including imaginary numbers. And we're going to talk about 2.5 on zeros of polynomial functions, which is maybe the biggest section of the entire course. It's big, but it wraps a lot of things together. It wraps together polynomial theory. And then we'll continue with chapter 2 next time on rational functions and algebraic functions, actually. Remember, your homework, and I got to deal with the grading in October, but your homework on chapters 2 and 3, okay, will be due Friday, October 9th. All right, but don't procrastinate. There's a lot to do here. Big homework set. Okay, remember, the next homework is worth a whole lot. Chapters 2 and 3 together, worth a whole lot. It's basically about the first two put together. All right, any general questions before we go on? Any general questions before we go on? All right, so let's get started then.
Hi, everyone. We're continuing with section 2.4 on complex numbers. But let's review section 0.9 on rationalizing denominators. So if you were asked to rationalize this denominator, the root 2 plus root 3, what would you multiply the top and the bottom by? You would multiply by root 2 minus root 3. I'm both the bottom and the top because we want to multiply by 1. But what do we call root 2 minus root 3? We called root 2 minus root 3 the what of root 2 plus root 3? It was the conjugate of the radical down to the denominator. And the goal ultimately was to rationalize the denominator. The goal was to rationalize the denominator, to make it nice. Now, in section 2.4, what if we're given an imaginary denominator? So let's say we have 1 over 2 plus 3i. Now, if we wanted to make the denominator nice, in particular real, usually rational, what would we multiply the top and the bottom by? We'd multiply by 2, and just like over here, we're going to flip the sign. 2 minus 3i on the bottom and on the top. Again, the goal is to multiply by 1 creatively in such a way that we're going to get a nice denominator. Real and preferably rational. And this here, 2 minus 3i, is called the complex conjugate of that denominator. Complex conjugate of the denominator. Again, the goal being to make the new denominator real and preferably rational. So we'll call it rationalizing the denominator, even though the immediate goal is to realize the denominator.
All right, so any questions before we go on? This was kind of a review and motivation. Any questions? Any questions? All right.
Hi, everyone. We've been talking about how to make denominators nice, whether it's by taking the conjugate of a radical expression or the complex conjugate of an imaginary expression. Let's talk about how complex conjugates help us. Now, before, we used to let x represent a real value. Now, more generally, we often represent a complex value by the letter z. So let z be a complex number. That is, let z be in the set C. Then z bar denotes the complex conjugate of z. So if z is written in standard form, a plus bi, where a and b are real numbers, then z bar is a minus bi, where we switch the sign on the imaginary part. So let's take a look at this table. If z is 3 minus 4i, what is the complex conjugate z bar? It's given by 3 plus 4i. And think about how these are related in the complex plane. How are they related? If you graph these two numbers as points in the complex plane, how are they related? Next, how about negative 1 plus 2i? Its complex conjugate is what? It's going to be negative 1 minus 2i. You only switch the sign on the imaginary part, not the real part. Here's a trick question. What's the complex conjugate of 5? Hint, what's the complex conjugate of 5 plus 0i? It's 5 minus 0i, or just 5. Bottom line, the complex conjugate of a real number is just itself. Finally, what's the complex conjugate of negative 4i? Well, here's a hint. What's the complex conjugate of 0 minus 4i? It's 0 plus 4i, or just 4i. By the way, sometimes in some books, when they write out numbers as complex numbers, they sometimes write 5 as 5 plus 0i and negative 4i as 0 minus 4i. I won't require that, but some books go into overkill and they actually do that. It's a very explicit standard form. All right, now again, how are these complex numbers related to their complex conjugates? Well, we get reflections about the real axis, this horizontal axis. So for example, 3 plus 4i goes to 3 minus 4i, and vice versa. Also notice that 5 over here, which is a real number, its complex conjugate is itself. So the numbers on the real axis are fixed points when you consider taking complex conjugates. The complex conjugate of a real number is itself. Okay, so once again, complex conjugates are used to help us make denominators nice. But how do they do that? How do they do that? In addition to the remainder theorem, this is one of the shortest theorems you'll find in pre-calculus. If z is a complex number, then z times its complex conjugate will be a real number. In other words, for any complex number c, zz bar is real. A complex number times its complex conjugate will be a real number. Here's a proof. Let z be of the form a plus bi, where a and b are real. That's standard form. And by the way, in many proofs in 200 level classes, we often start off with something like this. Let z be a plus bi, where a and b are real. Well, what's z times z bar? Its complex conjugate. It's going to be the number a plus bi times the number a minus bi. We're multiplying two complex numbers. Well, how would you multiply the factor a plus b times the factor a minus b old school? Well, remember, this is the factorization of a squared minus b squared. Or do your FOIL trick and know that the cross terms cancel out. But the result here is a squared minus b squared. So likewise, if you're multiplying this sum by this difference, it's the square of the first guy, it's a squared, minus the square of the second guy, the square of bi. Before we didn't have the i's. And we had a squared minus b squared. Now we do have the i's. And we have a squared minus the square of bi. You share the square here, and you get a squared minus b squared I squared. What was I squared? It was -1. Put parentheses here to remember that it's multiplied onto the b squared, or the opposite of b squared, over here. So ultimately, we're going to get what? We are ultimately going to get a squared plus b squared, where a and b are real. Well, the sum of the squares of two real numbers will be a real number. A squared plus b squared will be a real number. So therefore, ZZ bar is in the reals. And ultimately, we'll be able to realize or rationalize denominators. So notice this now. Yes, we've shown that z times z bar is a real value here, but look at this. Look backwards. A squared plus b squared is equivalent to all this back here. The factor a plus bi times the factor a minus bi. This is factoring. So for the first time, we're able to factor, that is, we're able to get a factoring rule for the sum of two squares. We had a factoring rule for the difference of two squares. Here it was, when you look at this in reverse. But now we have a factoring rule for the sum of two squares. We now have a rule for factoring the sum of two squares, which we didn't have before when we kept it real. But now, if we're allowed to use I, we can factor a squared plus b squared like so. And we're going to use this factoring rule a lot. So this set of equivalencies here shows why using complex conjugates is helpful to help us realize denominators, and also it gives us a factoring rule for a squared plus b squared. All right, next up, we're going to show how complex conjugates can help us divide complex numbers.
Okay, any questions thus far about complex conjugates and why when you multiply a pair of them, you get a real number? Also that factoring rule. Any questions? Any questions? Let's go on.
Hi, everyone. We're finally going to divide complex numbers. We're going to take the quotient of two non-zero complex numbers and express the result in standard form. And we're going to rationalize, or more precisely, realize the denominators with the help of perhaps complex conjugates. Now, the first step is to simplify all radicals. So, for example, if you see something like the square root of -7 or the square root of -9, make sure that you rewrite them with I and non-negative radicands. In step 2, we'll talk about different strategies on how you can realize a denominator. And remember, our result, our final answer, has to be in standard form. A plus bi, where a and b are real. Example. Let's simplify the following expression. We're dividing the complex number 4 minus I by the complex number 3i. We want to express the quotient in standard form. The result is a complex number that we want to write in standard form. Well, here's a question. What's a fast way of getting a real result? Remember, the goal here is that we want a real result, preferably rational. Now, we could use the complex conjugate, -3i, and multiply the top and the bottom, but we don't even have to be that ambitious. If we just want a real denominator, it would suffice just to multiply by I on the bottom and on the top. It might have to put parentheses here just to emphasize that the fraction bar groups the top and the I here, in fact, distributes. And by the way, if you want to make sure you get a positive denominator right off the bat, some people might actually want to multiply by -I on the bottom and the top, because then the denominator will be +3 in the end. But it's up to you. Okay, so let's take this expression and let's multiply by I over I. Again, the common theme here is that we're multiplying by 1 creatively. Well, I is the simplest thing that we can multiply 3i by, so we get a real denominator. And why is that? So on the bottom, we're going to get 3i squared, which will be real. What's 3i squared going to be? Well, when you multiply anything by I squared, you're taking its opposite, right? So that's going to end up being -3. The I up here, remember, is going to distribute. That's one reason why the parentheses might be helpful. You don't need them technically, but they're sometimes helpful visually. 4 times I is 4i, minus I times I is I squared. Don't do too much in your head, otherwise it's quite likely that you'll mess up a sign. Now, again, what is I squared? I squared is -1. So let's use that. On the top, we have 4i minus -1. It may be good to actually write that out. On the bottom, it might help to just write -3 immediately, but it is 3 times -1. Make sure you put 3 times -1. Don't write 3 minus 1. That's wrong. Either put parentheses or just say, hey, it's -3, the product. All right, on the top, we have 4i plus 1, and on the bottom, we have -3. Again, you can skip this and go straight to here. Now, we're not quite done yet because we have to write the result in standard form. A plus bi, where a and b are real. If b is negative, this will flip to a minus sign. All right. Well, first of all, we may want to split the fraction because we want 2 terms here. So let's split the fraction. And some of you might actually want to do an intermediate step. Put another step in here. So this here equals 4i divided by -3 plus 1 over -3. Now, if you look at 1 over -3, it should be evident that the -1 factor down here could pop out, and we get -1/3. The reason why this works is because 1 divided by -1 is -1. Okay. Normally, we don't like popping out factors from the denominator out here, but a -1 factor you can pop out for this reason. So we end up with -1/3 over here as our real part. Now over here on the left, we have 4i divided by -3. Again, the -1 factor on the bottom, we can pop out outside. So we get -4i over 3. And I realize this sounds kind of gross, but we also have the right to pop out the I. I is a factor of the top. We can pop out the I. So we end up with, over here, we have -4/3 times I. Bear in mind, if I is in the bottom, we cannot pop out the I straight up like that. But if I is a factor of the top, we are allowed to pop out the I like so. So once again, a -1 factor on the bottom, we can pop out on the side. But an I factor on the bottom, we cannot pop out to the side. An I factor on the top, however, we can pop out to the side. Right. Incidentally, 1 divided by I is -I, not I itself. All right. Anyway, we're still not quite done yet because we don't have the correct order. We have to switch the order of the 2 terms because we need the real part to be first. So the -1/3 goes over on the left, it's the real part, and then the -4/3 I goes over on the right. And finally, we have standard form. -1/3 minus 4/3 I. Again, the I should be popped out. This complex number divided by this complex number is this complex number in standard form. Next, we're going to talk about a more complicated example where we are going to need the complex conjugate.
All right. Any questions in the first example? Okay. Any questions here? Any questions? Let's proceed.
Hi, everyone. Before, when we were dividing by a pure imaginary number, the fix was very simple. But now, in our next example, the denominator is not pure imaginary. First of all, we need to rewrite this expression so that we simplify the radicals. What is the principal square root of negative 16? It is 4i. And what is the principal square root of negative 9? It is 3i. And we must simplify radicals immediately. So we have 4i over 4 plus 3i. Again, the denominator is not pure imaginary. So if we're going to realize or rationalize the denominator, we should multiply the top and the bottom by what? The what of the denominator. Again, the parentheses here can be helpful. Let's multiply by the complex conjugate of the denominator, which is 4 minus 3i. Multiply on the bottom and the top. We're multiplying by 1 overall. Again, we're multiplying by 1 creatively so that we can get what we want. In this case, a real denominator. All right, now, when we look at these denominators, when we multiply them together, there are different ways you can do this. The shortest way you can do this is to use the rule that we set up earlier in the notes. Remember, if z is the complex number a plus bi, and if z bar is the complex number a minus bi, so it's the complex conjugate of z, remember that their product is a squared plus b squared. If you're brave, go ahead and use that rule. It's very fast. Basically, it's going to be 4 squared plus 3 squared. And it doesn't matter if the minus sign is here and the plus sign is there. As long as you have split signs here, you're going to have the square of 4 plus the square of 3, which is 25. Now, if you're not comfortable using that rule, that's okay. You could use a more old school rule, such as this. Anytime you take the sum times the difference of the two same guys, you're going to have a squared minus b squared. The first guy squared minus the second guy squared. All right, so you get the square of 4 minus the square of 3i. That's fine. And that works out to be, in the end, 25. Of course, just like before, you should get the same simplified form for the denominator using all these methods. Or if you want to go even older school, you could use FOIL, the distributive property. 16 minus 12i plus 12i minus 9i squared. You see that the I terms cancel out, and you end up with what we get over here, basically. 16 minus 9i squared, which ends up being 16 plus 9, or 25. So regardless of the method, you should end up with 25. This rule gives you the fastest way of doing it, but the older school methods also work. Okay. So the denominator is 25. On the top, we end up with the product of these. We get that from the distributive property. 4i times 4 is 16i. 4i times negative 3i is negative 12i squared. And what is negative 12i squared? It's negative 12 times negative 1. That's going to end up being a positive 12. You don't have to show this step, but you should show this, that you get 16i plus 12 in the top, and we still have 25 on the bottom. Remember, the goal is to get standard form, a plus bi, where a and b are real. We have two terms here. Let's split the fraction. So we get 16i over 25 plus 12 over 25. Remember, the I on top can pop out. So we get 16 over 25 times I plus 12 over 25. We're not quite done yet. The real part comes first. Switch the terms, and we get that. This complex number divided by this complex number ends up being this complex number in standard form. 12 over 25 plus 16 over 25 times I. Next, we're going to talk about complex zeros of functions, including imaginary zeros, which is why we're bringing this stuff up now.
Right, because that's the point. That's why we're studying this stuff now in chapter 2. Any questions before we hit this? Any questions? Feel free to chat. All right.
Hi, everyone. Why are we bringing up imaginary numbers now? Because we're going to look at all complex zeros of a polynomial function, including potentially imaginary zeros. So for example, find all complex zeros of f where f of x equals x squared plus 9. Well, let's set y, or f of x, equal to 0, and solve for x. X squared plus 9 equals 0. Let's subtract 9 from both sides to isolate the square. And the square root method still works. We can say that x is plus or minus the principal square root of negative 9. The principal square root of negative 9 is 3i. So x could be 3i or negative 3i. Now the question was to find the complex zeros. So it would be enough to say that the complex zeros are 3i and negative 3i. In fact, if you were to just box these in, I may well accept that. If you're asked to solve this equation, then you should write the solutions then. But notice here, we have imaginary solutions to this equation. X squared plus 9 has two complex zeros, both of them imaginary. And notice they're related how? The complex zeros are complex conjugates. They are complex conjugates. And we're going to come back to that. All right. Next up, find the complex zeros of f, where f of x equals 2x squared minus x plus 3. If you try to factor that old school, to no avail. So we may have to resort to the QF, the quadratic formula. Now, it's helpful to identify what A, B, and C are. What are A, B, and C, the coefficients? Well, the leading coefficient, A, equals 2. Now, this is where a lot of people make a mistake. B is negative 1. Be careful about that. B is negative 1. And then C is 3. All right, let's apply the quadratic formula. You should remember this. X equals the opposite of B, so it's going to be the opposite of negative 1, plus or minus the square root of B squared minus 4AC. Remember, this was called the what? This was called the discriminant. This was a discriminant. And in fact, if you were to ask yourself, can I factor this old school? You might have wanted, that is factoring it over the integers, you might have wanted to work out the discriminant first. And you'll find out that the discriminant turns out to be a negative number. It turns out to be negative 23, which would tell you that you could not factor this thing old school. And you would have had to pretty much resort to the quadratic formula anyway. The thing is, if you work out the discriminant, you're ready to stick in the negative 23 right there in the radicand. So we pretty much had to use the quadratic formula anyway. By the way, it's the opposite of B, the opposite of negative 1, plus or minus the square root of the discriminant is negative 23, all over 2a, twice 2. When working out the discriminant, be careful. It's the square of -1. So we have +1 here. Minus 4 times A times C. So it's minus 4 times 2 times 3. 1, and then minus 24, that gets you -23. Remember, use grouping symbols here. Remember, the square of a real number is never negative. Use grouping symbols here. All right. The principal square root of -23 can be written as I root 23. Root -23 should be written as I root 23. Now, very often, if you're asked to find the complex zeros, we may be okay with this, but the thing is, over here, especially if I ask you to find the zeros and write them in standard form, okay? When in doubt, you might want to be safe and write the zeros in standard form. So here I split the fraction at the plus minus symbol. Right? Then I pop out the I over to the right. Technically, the I should be over here to the right. So in standard form, the complex zeros will be 1/4 plus or minus root 23 over 4 times I. By the way, up here, you could have written this as root 23 times I. What's the problem? Way too many students extend the radical too far. This would be wrong. So to avoid that, that's why I put the I in front, to the left. But if you write this, that's fine. Okay, so next, we are now ready in section 2.5 to talk about finding all complex zeros of polynomial functions. 2.5 is big. We hit that next.
All right, but you know what? Good time for a video. What do you think? And in fact, all right, ready for section 2.5 on zeros of polynomial functions. That's why I played that.
Hi, everyone. In section 2.4, we found complex zeros for quadratic functions. Now, in section 2.5, we're going to find complex zeros for higher degree polynomial functions. For now, we'll typically assume that f of x is a non-constant polynomial with real coefficients and written in descending powers. We'll go straight to an example we saw back in 2.3. Factor f of x, which is 4x cubed minus 5x squared minus 7x plus 2. And by factor, we mean factor completely. That's assumed. And we're going to find all of its real zeros. Now, first of all, notice that the GCF is 1. If the GCF were something different, factor it out. Now, you see this polynomial, and it has 4 terms. So you might consider something like factoring by grouping if you're lucky, but it does not appear that factoring by grouping will help us much. So we're going to resort to using the rational zero test, or the rational roots theorem, which is the theorem our little bird used back in section 2.3. Remember, we saw this problem before in section 2.3. But we needed the help of a little bird who had taken pre-calculus. This bird came into the room and whispered to us, tweet, tweet, hey, I think 2 is a 0 for this function. And then that helped to unlock the first door. It was the first key, and then we proceeded to factor f of x. But how did the bird know that 2 was a 0? Well, the bird was hoping that teacher was being nice and that at least one of the zeros for this thing would be a rational number, which is why the rational zero test or rational roots theorem was being applied. So you're hoping that teacher is nice and that at least one of the zeros here will be a rational number. Now, it would be really helpful if we could get a nice finite list of possible rational zeros. If this thing has a rational zero, what could it be? Is there a finite list that we could choose from? The rational zero test does exactly that. It allows us to list the candidates for the possible rational zeros of f. So here's how we apply the rational zero test, and then we'll discuss the theorem in general later on. So we focus on two key terms here. Once again, the constant term and the leading term. The constant term is 2 here. The leading term is 4x cubed. And really, we just have to focus on the leading coefficient, which is 4 here. So we're going to focus on the constant term and the leading coefficient. The constant term is 2. And we're going to call the factors of the constant term, or the divisors of the constant term, the possible values for p. Now don't worry about the way we label these factors, p and q. The main thing is we're going to consider the factors of the constant term here, and then later on, the factors of the leading coefficient over here, which will be the possible values for q. So the factors of the constant term are given by plus or minus 1 and plus or minus 2. The plus or minus symbols are important. Remember that the negative values are also possible. So the factors of the constant term 2 are plus or minus 1 and plus or minus 2. The factors of the leading coefficient 4 are plus or minus 1, plus or minus 2, and plus or minus 4. Now, the bottom line is that we're going to have, as our list of possible rational zeros, the candidates that we can get from this form. Now, some students might put a big old plus or minus in front. That's okay if you remember to keep putting it in. Otherwise, it might be safer to keep putting in the plus or minus symbols. The bottom line is that we need to have, in our format, factors of the constant term over factors of leading coefficient. The possible values of p over the possible values of q. So the factors of the constant term, plus or minus 1 and plus or minus 2, over the factors of the leading coefficient, plus or minus 1, plus or minus 2, and plus or minus 4. Again, you can think of this as a template that you can work off of. Never give this as your final answer, but this is a template that you can work off of. So let's get the various combinations we can get here. The various possible values of the numerator over the various possible values of the denominator. Let's start with the possible candidates with plus or minus 1 on top. So we get plus or minus 1, and then plus or minus 1 over 1 first, then plus or minus 1 over 2, and then plus or minus 1 over 4. So these 3 pairs of possibilities with plus or minus 1 on the top. And then consider the possibilities with plus or minus 2 on top. We have plus or minus 2 over plus or minus 1, plus or minus 2 over plus or minus 2, and plus or minus 2 over plus or minus 4. And then we simplify these fractions. So our simplified list of candidates will be plus or minus 1, plus or minus 1/2, plus or minus 1/4, plus or minus 2. Here we get plus or minus 1 again, but that's redundant. We already have plus or minus 1 over here. We don't need it again. And then plus or minus 2 over 4. Again, that's plus or minus 1/2, which is redundant. We don't need to list those again. So this is our list. Our list of candidates for possible rational zeros or roots of f. So if f here has a rational zero, it must be in this list. In particular, there's no way that 3 or 4 or negative 7/3 or something like that could be a rational zero because those numbers are not in this list. Of course, not all 8 of these could be zeros because it's only a third degree polynomial. It can have at most 3 zeros. But if it does have a rational zero, it's got to be in this list. As it turns out, this has 3 zeros, and they're all rational, and they're all in this list. Now, before we go further, I need to talk about how to generalize this. What theorem leads to this list of candidates? That's next.
So what I did was I thought it would be easier to apply this theorem first and then state it. Because if I had started with the statement of the theorem, your eyes would start bleeding. And we don't want that. So I know this seems like a lot, but I think the example was better to start with. Any questions about the example? Okay. Because now I'm going to generalize it. How do you generalize this?
Hi, everyone. Let's state the rational zero test or rational roots theorem, which is what the little bird applied to this polynomial over here to figure out the list of candidates of possible rational zeros for this function. Therefore, making it easier for the bird to guess that 2 is a 0, as opposed to, say, 3 or -1/3. So, for the rational zero test, or the rational roots theorem, which is more melodic, let's assume that f of x is a polynomial with only integer coefficients. So all of these a sub I guys must be in z, the set of integers. All these coefficients must be integers. And let's assume the polynomial is written in descending powers. The leading term over here on the left, the constant term over here on the right. And by the way, there will be a non-zero constant term, provided that you factor out the GCF first. Now, in our example, the GCF was 1. But if the GCF is, for example, x or x squared or something like that, then make sure you factor it out first and put that to the side. If x or x squared or so forth is a factor, then that means that 0 itself is a 0. And we're focusing on the other piece, not the GCF. So once you factor out the GCF, this will have a constant term, a naught or a sub 0, which will not be 0. For example, in our f of x example here, we had a positive 2 at the end. If each of the terms had an x in it, then you could factor out at least an x as part of the GCF. So remember, factor out the GCF first, and then we apply the rational roots theorem to the rest. We assume this is nth degree, so a sub n is not 0 here. And what then will form our list of candidates for possible rational zeros? So what will be our candidates? Or the possible rational zeros of f. Well, if f of x has rational zeros, they must be in the list of plus or minus p over q candidates, where p is a factor of a naught or a sub 0, the constant term, like 2 here, and q is a factor of a sub n, the leading coefficient, like the 4 here. So our candidates will consist of the list formed by when you take plus or minus factors of the constant term plus or minus factors of the constant term over factors of the leading coefficient. And that's how we get our list in our example. We're going to proceed with this example next time.
Right. Any questions? And don't worry, when I used to test students, I would never have people state the rational zero test. That would be sadistic. Basically, know how to apply it. Know how to apply it. Any questions before we proceed with this example? Any questions? Right. It's good to see how theorems look, though. All right.
Hi, everyone. Remember, in our example, we're trying to find all the real zeros for this polynomial function here. Now, from the rational zero test, or rational roots theorem, we found this list of candidates for possible rational zeros, and we're hoping that at least one of them will work. So how can we try these out? It's trial and error. And by the way, notice that positive one and negative one will always be in this list of candidates for a polynomial like this. So without even listing the whole list of candidates, you know that positive one and negative one are in the mix, and we could try them out. So for example, let's try positive one. Let's see if that's a zero for this function. Well, just by brute force, you could plug in 1 for x and see what happens. Do we get 0? So if we try k equals 1, and there's a reason why I'm calling this k. If we try k equals 1, we could directly evaluate f of 1 and see if it's 0. Plug in 1 for x. Notice that we end up basically adding all the coefficients. We get 4 minus 5 minus 7 plus 2, which is negative 6. So f of 1 is negative 6. The key thing to observe is that we did not get 0. We got negative 6. So what do? I've basically wasted your time. I'm kind of joking, but it doesn't help us to factor the function. Now, bear in mind, we do know something. If f of 1 is negative 6, that does tell us that what point lies on the graph. The point 1, comma, negative 6. If we plug in x equals 1, we get a function value, or y-coordinate, of negative 6. So that's nice to know that that point lies on the graph, but again, it doesn't help us factor this polynomial. Incidentally, in addition to direct evaluation, there's another way we could have evaluated this polynomial function. We could have used what? From 2.3. We could have used synthetic division. Put k equals 1 in the dunk tank. List out the coefficients. Make sure you put zeros if there are any missing terms. And these are based on the descending powers order. Bring down the 4. Multiply by 1, or k. Here, multiplying by 1 means you copy, right? So copy the 4. Add, you get negative 1. Copy, add, add. And again, this means that we're essentially adding all the coefficients. We end up with negative 6 again. And we find out that 1 comma negative 6 is on the graph, but that doesn't help us. 1 is not a 0. All right. So 1 didn't work for us. I've basically wasted your time, aside from these nice observations. Well, let's try k equals 2. Here's our list of candidates. Let's try k equals 2. Other students might try negative 1. That's fine. In fact, negative 1 would work as it turns out. As it turns out, 2 will also work. Again, we're following the thought process of our bird. Okay, who doesn't just have a bird brain? The brain's good enough to know pre-calculus. Let's try k equals 2 as our next candidate. Okay, now we could evaluate f of 2 directly, like we did for f of 1 over here, but it turns out that it will be much more efficient to use synthetic division, and we'll see why in just a moment. Well, let's do this. In fact, we've done this before, but here we have 2 in the dunk tank. That's our value for k. Here are the coefficients based on descending powers. There were no missing terms. Perform the synthetic division. I'll give you 30 seconds to remember this. All right, here we go. Bring down the 4. Multiply by k, or 2, we get 8. Add down, -5 and 8, we get 3. Think Vegas. If you lose 5 and win 8, you're still up 3. 3 times 2 is 6. Add, -7 and 6 is -1. Multiply by 2, we get -2. 2 and -2, hey, we get 0. Sometimes I put a smiley face in there, inside the 0. Why are we smiling? Because, well, here's why. By the remainder theorem, remember that? By the remainder theorem, we can then conclude that f of 2 is 0. Remember, in general, f of k equals r, the remainder. Here, f of 2 equals 0. Which means what? Which means that 2 is a 0 of f. If f of 2 equals 0, then by definition, 2 is a 0 of the function f. Which means what has to be a factor of f of x? What has to be a factor of this thing over here? If 2 is a 0, then what has to be a factor by the factor theorem? By the factor theorem, if 2 is a 0, then x minus 2 is a factor of f of x. Which means that, oh, and by the way, this verifies that the little bird was right. And by now you have the skills to either eat the bird or let it go free. Maybe you're vegan. So anyway, x minus 2 is a factor. We know 2 is a 0, so x minus 2 is a factor. So what does that mean? That means that that big ugly f of x guy that we started off with, this guy here, can now be written as the factor x minus 2 times another factor. Now, folks, remember, when we factor, we do what D word? We factor, we divide. When we factor, we divide. How do we get this other factor over here? We take the f of x guy over there, and we divide by x minus 2. We've done this before in section 2.3, by the way. I'm reviewing. Because remember, if I ask you, 10 is 2 times what? 10 is 2 times 5. Because 5 is 10 divided by 2. We divide to get the other factor. F of x divided by x minus 2. Now, how can we do that? How can we take a polynomial in x and divide by x minus 2? We could use synthetic division. But wait, we've already done that. Which is why, if you want to know if 2 is a 0 for f of x, although you could plug in 2 directly, as we did with f of 1 over here, and you would find that f of 2 equals 0, by the way, in a way, you're not taking full advantage of synthetic division, because with synthetic division, you're killing 2 birds with 1 stone. Aha, more with the birds. So here, when you perform synthetic division, not only are we verifying that f of 2 equals 0, but if 2 works, and here it does, it also gives you an important clue as to how to factor f of x if 2 works. 2 does work, and this helps us factor. In fact, it gives us the other factor. If 2 works, we know that x minus 2 is a factor. From the synthetic division process, we get the other factor. Now remember, we started with a third-degree polynomial. If you take a third-degree polynomial and you divide it by a first-degree polynomial, the result is going to be what degree? It's going to be second degree. A third degree, in this case, divided by a first degree, is second degree. So the leading coefficient 4 here is going to lead to 4x squared is going to be a second degree factor. Plus 3x minus 1. There's a zero remainder. There's no fraction. Remember, we used to have a fraction here. Remainder 0, we don't have that. So the quotient here, this polynomial quotient, is going to be this other factor here. 4x squared plus 3x minus 1, that's this other factor over here. We have this. F of x, that third degree guy we started with, equals the factor x minus 2 times this other factor, this quotient we got when we performed synthetic division. If you're desperate, you can use the quadratic formula, but it turns out this does factor old school. So you could use a quadratic formula or factor old school over the integers. So we get f of x equals, don't forget x minus 2 from before. We got that because 2 is a 0. Remember, this worked. F of 2 got us 0. X minus 2 is a factor. And then old school, this quadratic, this cutie factors as the factor 4x minus 1 times the factor x plus 1 in either order. Then we can get all the real zeros, set each factor equal to 0, and we get the real zeros for this thing. So the zeros, real zeros, are going to be 2, 1/4, and -1. So these are all of the real zeros, and therefore all the zeros of the third degree polynomial. Okay, again, if we're desperate, we could use a quadratic formula. We don't have to rely on rational zeros anymore. But it turns out all 3 zeros are rational. Incidentally, notice that all 3 zeros, they were rational, and all 3 of them were in this list. Notice that positive 2 is in the list, positive 1/4 was in the list, and -1 was in the list. They had to be. If a rational zero works for a function, it's got to be in this list from the rational zero test or rational roots theorem. All 3 of these would have worked. So if you had picked 1/4 instead of 2 or -1, that would have worked out. The factorization would have looked a bit different, but it would have worked out. All right. These are the zeros once again. The real zeros of a function in the xy plane correspond to what points on the graph? They correspond to the x-intercepts. We have x-intercepts at 2, 0, 1/4, comma 0, and -1, comma 0. And because all of these zeros have multiplicity 1, because these were the exponents on the corresponding factors, 1 is an odd number. Therefore, at each of these x-intercepts, we do what? We cut like a snake. On Desmos, here's a nicer graph. For y equals 4x cubed minus 5x squared minus 7x plus 2. Here's a nicer graph. We have the 3 x-intercepts here in blue, green, and purple. And at each x-intercept, we cut. The function values, or y-coordinates, cut from negative to positive. And then here, at the green, from positive to negative. And at the purple point, from negative to positive. So again, we know the sign of f everywhere is going to be negative. The function values, or y-coordinates, will be negative here, 0 at this x-intercept, positive here, 0 at this x-intercept, negative here, 0 at this x-intercept, positive over here. So we know the sign of f for every value of x, every real value. The leading term is 4x cubed. We know it's a rising snake overall. Rising up to the right, falling down to the left. Okay. Also, if you're able to do a graph of this, on even a graphing calculator beforehand, you might be able to guess what the rational zeros are if you have a sketch graph beforehand, maybe from a graphing calculator or basic software. Okay, so next up, we're going to talk about some last observations about the rational zero test or the rational roots theorem.
Yeah, kind of thinking about how the theorem works. Yeah. The number of zeros, you mean? The number of zeros. Well, we're going to find from the fundamental theorem of algebra that an nth degree polynomial with real coefficients, and not just a constant, will have n complex zeros. Okay? Some could be real. Some could be copies. That's a deep theme, actually. So you asked a big question, and we're going to deal with that. It's true the number of distinct zeros can be less than the degree. The number of real zeros can be less than the degree. But there are n complex zeros, okay? The degree number of complex zeros. But there are subtleties. Okay, but good question. We're going to deal with that deeply. Next, I'm going to make some last-minute observations and test your critical thinking. And then we'll take a break after this next video.
Hi, everyone. Let's discuss in further detail the rational zero test or the rational roots theorem. Remember that the template for the list of possible rational zeros, the list of candidates, is given by plus or minus factors of the constant term over factors of the leading coefficient. Now, 4 questions for you. 4 questions. First of all, what is the most common error when getting the list of candidates? The most common student error. This is more of a student question than a math question. Second, if a candidate works as a zero in the synthetic division, can it work again? So if a number works in the dunk tank and you get a remainder of 0, can it work again when you get the corresponding quotient? If a candidate does not work as a 0, can it ever work down the line for one of these quotients down here? Number 4, does the theorem apply to f of x, where f of x is x squared minus 3? So consider these 4 questions regarding the rational zero test or rational roots theorem. I'll give you a minute. All right, what's the most common student error when getting the list of candidates? Is that students take the reciprocal. They switch or flip the fraction around. The problem is that students often do this. Don't do that. Don't switch. Don't try to take reciprocals. Now, one way to remember which way it goes is to use a simple example, such as x minus 2. Remember that if you have x minus 2, there's an implied 1 out in front. So what would be the list of candidates? Now, some students might think, oh, is it the factors of 1 over the factors of negative 2? Does it go plus or minus 1 over plus or minus 1 or plus or minus 2? Or could it be the factors of negative 2 over the factors of 1? Plus or minus 2 plus or minus 1 over plus or minus 1. Well, here's the deal. What is the only rational zero of x minus 2? The only rational zero is given by 2. Well, how can we get 2? Can we get a 2 from here? Nope. You can't get a 2 from here. You can only get a 2 from here. So it better be factors of -2 over factors of 1 and not vice versa. So just like with factoring and long division, think about a basic example. And that'll help you remember to not switch these, to not take the reciprocals. Again, that's the most common student error. If a candidate for a rational zero in the synthetic division works, can it work again? And the answer to that is yes. The answer to 2 is yes. Here's an example. Well, imagine a polynomial that factors as x minus 2 all to the 10th. Well, guess what? If you take this guy, if you put 2 in the dunk tank, you're going to get 0 as the remainder, so it works out. And you get the quotient here. You have x minus 2 times this quotient over here. This quotient over here will be the equivalent of x minus 2 all to the 9th. And in fact, if you keep going, it turns out that you can put 2 in the dunk tank 10 times and it'll work out. You'll get a 0 remainder. If you don't believe me, take something like this. Take something like x squared minus 4x plus 4. That's a PST. I hope you recognize that as the square of x minus 2. Apply synthetic division with k equals 2. Do it twice, see what happens. This is just the extension of that. Third, if a candidate does not work as a 0, can it ever work? The answer to that is no. Imagine a polynomial up here, and 2 is not a 0. 2 is not a 0. Let's say it's a polynomial in x. That means that x minus 2 is not a factor. Well, imagine factoring this thing further over the reals. That times that, and then this may factor as that times that, and so forth. Well, here's the thing. If x minus 2 is not a factor of the big guy, it's not going to be a factor of any of these smaller guys, these lesser degree guys down here. So if 2 is not a 0 up here, x minus 2 is not a factor up here, and therefore 2 is not a 0 down here, anywhere. X minus 2 is not a factor for any of these guys down here either. 4. Does the theorem apply to x squared minus 3? Actually, the answer is yes, but. Yes, it's of the right form, right? We have a polynomial in descending powers, integer coefficients. So the theorem applies. What the theorem says is the following. It says if this has rational zeros, they have to be in this list. So it would have to be in the list plus or minus 1 or plus or minus 3. Remember, it's got to be plus or minus factors of the -3 over factors of the 1 over here. So if this thing has rational zeros, it's got to be either 1, -1, 3, or -3. Well, none of them work. The only zeros for this thing, the only zeros for f are √3 and -√3, which are not rational. So here's the thing. The theorem applies. It's true that if it has rational zeros, it's in this list, but this thing has no rational zeros. So none of the numbers in this list worked. All right. So the theorem applies. It's just that none of the zeros were rational. So it didn't help us any in terms of cracking this thing. All right. Next up, we're going to talk more about factoring.
All right. So now is a great time. Actually, now is a great time for a break. Wouldn't you agree? I have 8:17. Let's take a break until 8:28. All right. So remember to mute, especially if you're using the restroom. I admit, even on campus, I forget that sometimes. It's very embarrassing. like that Leslie Nielsen film, The Naked Gun. 9:28, mute, and I'll record when I get back. All right, I'll do it 8:28. I guess 8:29. Make it 8:29. All right. Recording. Okay, so we're gonna start up again. All right, factoring. More on factoring.
Hi, everyone. Let's talk factoring. So let's say that you're told to factor some polynomial. And you could use the rational zero test and synthetic division to maybe plot some factors. It could be a successive process. And in fact, in the rational zero test, you can keep updating the list of candidates. Maybe you can eliminate some along the way. And by the way, if you get something like x to the fourth minus 1 down the line, then you could be able to factor that directly and get away from the synthetic division. But let's say you can get it all the way down to a quadratic. Well, are you done? It depends on what set you're factoring it over. See, this is how you can be a smart aleck with your old algebra teacher. Let's say you run into your old algebra teacher on the street, and your algebra teacher says, hey, I have a quadratic for you. Factor this. Now you can be a smart aleck and ask, over what set? And then maybe your algebra teacher will disappear in a cloud of smoke. Because it depends. What set of coefficients are you allowed to factor over? See, in old school factoring, what your algebra teacher would be expecting is factoring over the integers. For example, if you see something like the factor 3x plus 1 times the factor x minus 2, this is an example of factorization over the integers, because all the coefficients in each factor are integers. Positive 3, positive 1, positive 1, negative 2. However, after your algebra class, you may be asked, including in this class, you may be asked to factor a polynomial over other sets. Maybe the rational numbers, Q, maybe the real numbers, R, maybe the complex numbers, C. And when we say factor, we mean factor completely. Factor as much as you can, given that you're allowed a given sandbox of numbers. If you're allowed to play in C, then there may be all sorts of ways you can break things down. And we'll see that. So again, here's an example of old school factoring over Z, the set of integers. Our old friend, 4x cubed minus 5x squared minus 7x plus 2. We've just shown how you can factor that over the integers, where each of the factors have all integer coefficients. 1, negative 2, 4, negative 1, 1, and 1. And even though we saw new procedures, still the result was basically old school factoring, factoring over the integers. But let's say you were told to factor over Q, the set of rational numbers. Well, this would be acceptable. This would also be an example of factoring over Q, the set of rational numbers, because each of these coefficients in each of these factors is not only integer, each coefficient is also a rational number. But if we're allowed to factor over Q, there may be other forms we prefer. So for example, if you look at this factorization, you can immediately read off the integer zeros. 2 over here, and negative 1 over here from this factor. But over here, we don't have an integer 0. We do have a rational 0, though. And how can we make that clearer. We could factor out a 4. Take the 4x minus 1 and factor out a 4. When you factor, you do what? You divide. So how can you factor 4x minus 1? You can factor it as 4 times the quantity x minus what? When you factor, you divide. X minus 1/4. Now, in old school factoring over the integers, that would not be allowed. But if you're allowed to factor over q, we often prefer to factor 4x minus 1 as 4 times this. And then we put the 4 out in front. So then the factorization would look like this, where the 4 is out in front, that's the leading coefficient, and then the factor x minus 2, then the factor x minus 1/4, then the factor x plus 1. Although, of course, you could reorder these factors. The 4, however, would normally stay out to the left. Now, this is in a certain form called Lft form, which we'll talk about later on. Lft stands for linear factorization theorem. We'll talk about that later on. It turns out that if you're allowed to factor over C, the most ambitious set, then you can get a form like this for any polynomial of this kind of form. So Lft form, in this case, we've factored over Q. All right, and one advantage of this is that we can immediately identify 1/4 as a 0 as well, just from the factorization. Whereas here, if you saw the 4x minus 1, it may have had to take you a few steps or some thought to figure out that 1/4 was a 0 based on this factor. Here, when you break it up like 4 times this, 1/4 is clearly a 0. So the rational zeros you can see are 2, 1/4, and -1. All 3 zeros for this cubic turned out to be rational. All right. What if we're more ambitious? What if we're allowed to factor over the reals? X squared minus 3. Now, in the olden days, in your algebra class, what would you tell your algebra teacher if your algebra teacher asked you to factor x squared minus 3, old school? You'd say, it's prime. I cannot factor it any further. X squared minus 3 is prime or irreducible. We cannot break it down any further. And 1 times doesn't count, okay? We cannot break it down any further over Z, or for that matter, over Q. You cannot factor it over the rationals either. You'd have to go out to something like the reals in order to be able to factor this. And how could you factor this? Well, we can think of this as a difference of 2 squares. It's just that 3 is not a very nice square. It's not a perfect square. But you could factor x squared minus 3 as x plus something times x minus something. 3 is the square of what number? It's not very nice, but it is real. The square root of 3. So we can treat x squared minus 3 as a difference of 2 squares, maybe not nice squares, but a difference of 2 squares. X squared minus 3 can be factored like so, or vice versa. You can switch the factors. The factor x plus root 3 times the factor x minus root 3. Now, the square root of 3 is not an integer, and it's not rational. So these kinds of factors would not be allowed if you were told to factor over Z or Q, but if you were told to factor over R, the reals, or over C, the complex numbers, then you'd be expected to break this down further. Remember, when you're told to factor, you must factor completely over the given set. All right. And we can see immediately that negative root 3 and positive root 3 are real zeros. One advantage to factoring over a given set is that you tend to be able to get the corresponding zeros in that set. All right. Now, C, the most ambitious set, the set of complex numbers. And in fact, if you're allowed to factor over C, if you take a polynomial in a nice form, then you should be able to break it down into Lft form. basically a number times a bunch of linear factors. All right. Again, this is Lft form. But these are all linear factors. First degree. All right. Now, a key thing that's going to help us factor polynomials over C is the fact that we now have a rule for factoring the sum of two squares. We got this from section 2.4 because we needed imaginary numbers. We can factor a squared plus b squared as the factor a plus bi times the factor a minus bi. It looks a lot like the factorization for a difference of two squares, except you must insert the i's. All right, so for example, how'd you factor x squared plus 9? I'll give you 15 seconds. All right, first of all, you might want to consider how do you factor x squared minus 9? That's a difference of two nice squares. We can factor that old school as the factor x plus 3 times the factor x minus 3, or vice versa. But now, in red, what happens if we have x squared plus 9? How do we change the factorization? It's going to be the factor x plus 3i times the factor x minus 3i. So many students might want to start with considering the difference, and then when you go to the sum, insert the i's. X squared plus 9 equals the factor x plus 3i times the factor x minus 3i. All right. And again, we can identify negative 3i and positive 3i as zeros, complex zeros. All right, next up, we're going to factor a polynomial like this completely. It's a fifth degree. We can factor it completely over, say, the reals and over C.
Okay, any questions thus far? The key theme in this video was how to factor over varying sets. And on a homework or potentially a test question, I'll typically say factor over this set, Z maybe, or R or C. Questions? Questions? All right.
Hi, everyone. In this example, we're going to factor this fifth degree polynomial over the reals, R, and find all of its real zeros. And then we're going to factor this polynomial over C and find all of its complex zeros. Okay, so first off, when we factor this, what is the first thing we factor out? We normally try to factor out its GCF first. What is the GCF? Here, the GCF is x. Notice that if there is no non-zero constant term here, that x is probably a factor. So the GCF is x. We factor it out. When we factor, we divide. We factor out the x, and then notice that each of the exponents goes down by 1. In another factor, we get x to the fourth plus x to the second minus 6. Now here, we have a fourth degree polynomial. And you might be afraid. You might wonder, are we stuck? But we're not, because this fourth degree polynomial is in what form? It is in quadratic form. And why is that? Because when we try the substitution, u equals x squared, the middle power of x, we end up with a cutie, a quadratic trinomial. Notice that the leading exponent, the 4 here, is twice this exponent, the 2. And then negative 6 is a constant term. So when you apply the substitution, we end up with x times the quantity u squared plus u minus 6. And we factor this Cutie in u. So when we do that, we have, don't forget the x, and then we have the factor u plus 3, and then the factor u minus 2, or vice versa. Don't forget, we have to go back to x. U is x squared. Let's go back. We have x, don't forget, the factor x squared plus 3, and the factor x squared minus 2. Now, you didn't have to do the substitution. You could have gone directly from here to here. Remember that you have x squareds here and not x's. But you could have gone directly from here to here without going through the substitution, although the substitution does help many students. Now, at this point, we have factored this completely over z, the set of integers, or for that matter, q, the set of rational numbers. We factored over z, the set of integers, or q, the set of rational numbers. All right, but if we wanted to factor this over the reals, and that was the instruction here for us to factor over the reals, what else could we factor? Well, the x is just a nice linear. It's just an x. Over here, x squared plus 3. Well, here's a hint. Here's a hint. Now, this is for a quadratic specifically. A quadratic can be factored over the reals, the set of real numbers, if and only if it has real zeros. That's true for quadratics.
I'm assuming that you factored out the GCF, by the way.
Well, x squared plus 3, does that have any real zeros? The answer is no. And by the way, we're appealing to the factor theorem here. If k were a real zero, then x minus k would be a factor. But now what about x squared minus 2? Well, x squared minus 2 does have real zeros. And you can think of this, in fact, as a difference of two squares. Maybe not nice squares necessarily, but the difference of two squares. How could you factor x squared minus 2? You can factor it as the factor x plus root 2 and the factor x minus root 2. 2 is the square of the square root of 2. And at this point, we have completely factored the fifth degree polynomial over the reals. Now, from these factors, we are able to get the real zeros. What are the real values of x that will make this equal to 0, this equal to 0, and this equal to 0? Well, x equals 0 makes this factor 0. Negative root 2 makes this factor equal to 0, and positive root 2, when plugged in for x, makes this factor equal to 0. And we have no real zeros coming from here. Notice this quadratic, x squared plus 3, is quadratic, and it's prime or irreducible over the reals. X squared plus 3 is a quadratic that is prime or irreducible over the reals. All right. So we have the three real zeros here at x equals 0, negative root 2, and positive root 2. Now notice that each of these has multiplicity 1 on the factors. And remember, these real zeros correspond to what points on the graph of y equals this fifth degree. Remember that the real zeros of the function correspond to the x-intercepts of the graph. So if we're to graph this thing, y equals this fifth degree, what would it look like? I'll give you 15 seconds. Sketch a graph. All right, folks. Remember, these correspond to x-intercepts over here, the zeros, 0, and plus or minus root 2. All right, so let's graph this thing. Y equals x to the fifth plus x to the third minus 6x. Because the leading term is x to the fifth, we have a rising stake in the long run. And because the factorization looks like this, again, we have x-intercepts at 0, 0, at negative square root of 2, 0, which is negative square root of 2 is about negative 1.4, and positive square root of 2, 0. And notice that at each of these x-intercepts, the graph will cut. Cut like a snake, cut like a snake, cut like a snake. And that's because the multiplicities on these factors are odd. They're ones. And we're not going to discuss the s squared plus 3 right now. Notice something else. What kind of function is this? Where f of x equals x to the fifth plus x to the third minus 6x to the first. We have here an odd function, which means that the graph is going to be symmetric about the what? About the origin, 0, 0. Notice that the origin is a point on the graph. It has to be for any odd function where 0 is in the domain. And notice that we do have symmetry about the origin. If we were to take this snake, rotate it 180 degrees about the origin, we get the same snake. Odd function, symmetry about the origin. So we know a lot about the graph of this thing. Now, what are a couple of points that we cannot locate just yet? We're going to need calculus. Well, we're going to need calculus for the local max point over here and the local min point over here, the turning points. In calculus, you're going to set the derivative equal to 0, solve for x, and that will help you find the turning points here. All right, so just from the factorization over the reals, we can basically graph this thing very well. Next, we're going to talk about the factorization over C, the set of complex numbers, and some patterns.
All right, so that's the factorization over R. Next, we're going to talk about the factorization over C. Any questions? Any questions?
Hi, everyone. Let's now factor our polynomial over C, the set of complex numbers, and find all of its complex zeros. That's a typo there. So we've already factored this polynomial over R, the set of real numbers. Which of these factors can now break down over C? X is good. These two other linear factors are also good. Is this prime or irreducible quadratic over the reals that we can break down further? X squared plus 3. How can we factor it over C? Well, look at it this way. What if we had to factor x squared minus 3. If we had to factor x squared minus 3, we could factor that as a difference of two squares. Maybe not nice squares, but squares. We would factor x squared minus 3 as x plus what? And x minus what? 3 is the square of what number? The square root of 3. But now wait a minute. We want to factor x squared plus 3, not x squared minus 3, which means we have to insert what? Much like a scientist, we have to insert the i's. I over here, or you can move it in front of the radical. That might be safer. I over here, or move it in front here. So how can we factor x squared plus 3? It now breaks down over C as a product of these two linear factors. X plus I root 3 and x minus I root 3. So now, notice that when we factor this fifth degree polynomial over C, we're now factoring it as a product of 5 linear factors. And that's not a coincidence. Also, what are the 5 complex zeros? Well, we already got the 3 real zeros from earlier when we factored over R. Because x was a factor, 0 was a 0. Because x plus root 2 is a factor, negative root 2 is a 0. And because x minus root 2 is a factor, positive root 2 is a 0. But now, since x plus I root 3 is a factor over C, negative I root 3 is a 0. And because x minus I root 3 is a factor, I root 3 is a complex 0. So these are the 5 complex zeros. Okay, and the fact that our list of complex zeros looks like this, it's not a coincidence. There are several patterns that do extend to theorems. We'll talk about those theorems next time.
Okay, pause. Oh, okay, pause here. Now factoring. Okay, so x squared plus 3 is prime over the reals, but it wasn't over C. We factored it. And right, a squared plus b squared, that factors as a plus bi and a minus bi. Right, that's right. Any other questions? Any other questions? All right.
Hi, everyone. Look at our previous example and take 30 seconds to answer these 3 questions. Look at these 5 complex zeros. In particular, look at these 2, the negative I root 3 and the I root 3. How are these 2 complex zeros related? Second, why does it make sense that we have 5 complex zeros here? And number 3, describe these factors in X when we factor over C. The answer is right in your face. Go ahead and answer these 3 questions, and we're going to extend these later on. Take 30 seconds. All right, how are negative I root 3 and I root 3 related? They form a pair of complex conjugates. And in general, this is true, that if a complex number is a 0 for a polynomial function with real coefficients and all that, then its complex conjugate will also be a complex 0. For example, look over here. When we looked at x squared plus 9, its two zeros, 3i and negative 3i, formed a pair of complex conjugates. When we looked at this cutie, this quadratic trinomial, its zeros formed a pair of complex conjugates. In general, we have this theorem, the complex conjugate pairs theorem. So if f of x is a polynomial with only real coefficients, then a complex number z, say a plus bi, is a zero of f of x if and only if its complex conjugate, z bar, or a minus bi, is also a zero of f of x. So over here, if we know that I root 3 is a complex zero for a polynomial function with real coefficients, we know that its complex conjugate partner, negative I root 3, must also be a complex zero. Bear in mind that the complex conjugate of a real number is itself. So if root 2 is a complex zero, then root 2 is a complex zero. We're not saying anything extra, but it does not contradict the theorem. If z is a complex zero, then so is z bar. Well, the complex conjugate of a real number is itself anyway. Okay, so this pattern is true in general for all polynomials with real coefficients. Now, number 2, why does it make sense that we have 5 complex zeros? Well, it's because the original polynomial is 5th degree. It has degree 5. And that takes us to what's called the Fundamental Theorem of Algebra. This is in part 2 of my notes. By the way, in green, I discussed the Fundamental Theorem of Arithmetic and also of Calculus. But the Fundamental Theorem of Algebra says that if f of x is a non-constant nth degree polynomial, etc., in descending powers with real coefficients, then it must have exactly n complex zeros. So, for example, since we have a 5th degree polynomial with real coefficients in this nice form, there must be 5 complex zeros, some of which may be real. Remember, complex numbers include real numbers. The zeros may or may not be real, and the zeros may be repeated based on their multiplicities. So, for example, a double root or double zero is counted twice. A double root or a double zero is a zero of multiplicity 2, and it will be counted twice. A zero of multiplicity 3 will be counted 3 times, and so forth. So zeros are counted according to their multiplicities. For example, if you have something like x minus 2 all to the 10th, then 2 would count 10 times. 2 is a zero of multiplicity 10, and the 10 complex zeros are all named 2. But there's only one distinct complex zero. 2 is the only distinct complex zero, but in general, it's a zero of multiplicity 10. I'll put that note down here. So again, for x minus 2 all to the 10th, 2 is the only distinct complex zero, the only different one. There's only one distinct one. There are no others. But if you go beyond the distinct issue, there are 10 complex zeros. They're all named 2. 2 is a zero of multiplicity 10. Likewise, for x to the 100th, 0 is a zero of multiplicity 100. Third, describe these factors in x where we factor over c. I'm referring to this factorization over here. I have it right here. We have here a product of 5 linear factors. Bear in mind that if the leading coefficient were not 1, then we would have that leading coefficient in front over here. So we could have a constant factor as well. The linear factorization theorem, the LFT, if f of x is a non-constant polynomial in descending powers with real coefficients, and let's say it's nth degree, then it must have a factorization into linear factors over C of this form. So basically, when you factor this nice polynomial over C, you get this form for the factorization called Lft form. All right, so again, f of x equals, well, whatever the leading coefficient is, you could put it here. Here the leading coefficient was 1, so we didn't write it down. But if the leading coefficient were 2, 3, -6, whatever, then the leading coefficient would go here. Of course, it's a real non-zero number. And then you would write down these linear factors, which are all of the form x minus a complex zero of the function. Remember, a fifth degree polynomial of this type will have 5 complex zeros. And the factors can be listed out as x minus the first zero. There's no order, but you can pick the order. X minus the first zero, and then x minus the second zero, and so forth. And last, x minus the last zero. So over here, again, you can pick the order. If the first zero is 0, we have x minus 0, or just x, as our first linear factor. Since this is a 0, that's a factor. Since that's a 0, that's a factor. Since that's a 0, that's a factor. Since that's a 0, that's a factor. The factor theorem is related to this. And again, if you have copies of the same 0, if you have a 0 of multiplicity more than 1, they can put exponents like squares and cubes and so forth. So for example, for x to the 100th, you can think of 100 copies of x minus 0. But I'll accept this as Lft form. You don't have to write all this out. Now let's do another example of Lft form. So let f of x be x to the 5th minus 8x to the 4th plus 16x cubed. First of all, let's factor out the GCF. The GCF is x cubed. And then when we factor, we divide. The other factor is x squared minus 8x plus 16. The exponents go down by 3. Now, x cubed is still there, but notice x squared minus 8x plus 16 is a nice PST, a perfect square trinomial, which can be factored as the square of x minus 4. Now, if you want to be a real stickler and stick to the form, you could write this factorization as the leading coefficient 1 times, well, x can be written as x minus 0. Since the x is cubed, we could write that 3 times. We have x minus 0, and then do 2 more copies. So x cubed could be written like this if you really wanted to fit the form precisely. And then the square of x minus 4, well, the square of x minus 4. We have 2 copies of x minus 4. So if you really wanted to stick to this Lft form here, you could write it like this. But if I wanted Lft form, then I would accept this as Lft form. X cubed times the square of x minus 4. So this polynomial has 5 zeros. Their names are 0, 0, 0, 4, and 4. There are only 2 distinct zeros, 0 and 4. 0 is a 0 of multiplicity 3. 4 is a 0 of multiplicity 2, because 0 counts 3 times and 4 is counted twice. Remember when we factored our old friend here, 4x cubed minus 5x squared minus 7x plus 2, we put this factored form in Lft form. The linear factors over here, x minus a 0, x minus a 0, x minus a 0, and the leading coefficient was over here, the 4. You need that leading coefficient there. Otherwise, if you were to multiply these things out, the leading term would be x cubed, not 4x cubed. You need the leading coefficient here in order to rescale this thing properly, so that 4x cubed is the leading term and these other terms are also appropriate. You need this 4 to rescale this. A final note, how is factoring over R different from factoring over C? Well, sometimes when you're factoring over R, you can get stuck on these prime or irreducible quadratics over the reals. So, for example, in our example up here, when we had x to the 5th plus x cubed minus 6x, when we factored over R, the reals, way up here, remember, we got stuck at the x squared plus 3. The leading coefficient was 1, and these other factors were linear, but we got stuck at the x squared plus 3. If we're factoring over the reals, we're sometimes not able to break up some quadratics, namely the quadratics that are prime or irreducible over the reals. Prime, irreducible, quadratic over the reals. We get stuck there sometimes. But if you're allowed to factor over C, then even guys like these eventually have to break down. And it did. So what's one reason why we like C? Because when we have C, we get a nice form for the factorization, the Lft form for the factorization, where we have maybe a constant and a bunch of linear factors, which can clearly indicate the zeros, the complex zeros. Okay, next up, Descartes' rule of signs. This is another rule that allows us to try to figure out information about the kinds of zeros that we have.
All right, so our last part here, our last video, but 9 minutes. Any questions? Any questions? Here's another rule that can help you give you hints about the nature of these real zeros. Real zeros, positive versus negative.
Hi everyone, remember when we found possible numbers of turning points for the graph of a polynomial? Well, now we're going to talk about Descartes' rule of signs, which will help us figure out possible numbers of positive real zeros and negative real zeros, accounting for multiplicity. So a double zero counts twice, for example. Okay, first off, let's assume that f of x is a polynomial with real coefficients and written in descending powers, as usual. And remember to factor out the GCF first, if it's not 1. So for example, if you see x cubed plus x squared, make sure you factor out the x squared first, and then you'll deal with x plus 1. This guarantees that we have a non-zero constant term in here, a sub 0. The same went for the rational zero test or rational roots theorem. We need a non-zero constant term in there. And actually, you don't have to worry about missing terms. Now we're going to use this idea of variations in sign. The number of variations in sign in f of x, written in descending powers, is given by the number of sign flips. So instead of the fancier term variations, I might just refer to sign flips. And we're focusing on the non-zero coefficients as they're read from left to right in the descending powers form. So we're going to focus on these variations in sign, or sign flips, in the descending powers form. Let's go straight to our old example. F of x equals 4x cubed minus 5x squared minus 7x plus 2, our old friend. Now, what if we wanted to apply Descartes' rule of signs? What if we didn't know the zeros already? What if we wanted to apply this rule? First of all, we'd want to count the number of variations in sign, the number of sign flips. Variations in sign, that is the number of sign flips in this descending powers form. It may be helpful to put a positive sign in front of the 4 because 4 means positive 4. How many sign flips do we have as we read this from left to right? From positive to negative, that's a sign flip or a variation in sign. That's why I put the positive sign in front here. We do not have a sign flip here. We do have a sign flip here from negative to positive. So we have 1, 2, variations in sign. One, two. So what does that mean? That means that, I use a bit too much notation here. This means that the possible number of positive real zeros of f could be, we'll start with 2, which is the number of sign flips, and then count down by 2s. Similarly to the turning points, the number of turning points. Count down by 2s. Stop before you hit negative numbers. Because you cannot have a negative number of positive real zeros. So we start with 2. 2 minus 2 is 0. And we stop there because you cannot have negative 2 positive real zeros. So the possible number of positive real zeros of f could be 2, the number of sign flips or variations, or if you count down by 2, it could be none. There could be no positive real zeros. So what are some possibilities in general? What are some examples of polynomial graphs that have 2 or 0 positive real zeros? Okay, so here's our old friend, right? Y equals this over here. It turns out that we are going to have 2 distinct positive real zeros. These correspond to the x-intercepts to the right of the y-axis. We have here 2 distinct positive real zeros, each with multiplicity 1. So that's one possibility. And in fact, we do get 2 positive real zeros, each with multiplicity 1. But in principle, we could have gotten something like this. Y equals the square of x minus 4, for example, where 4 here is a positive real zero of multiplicity 2, and we get a bounce. So remember that we take multiplicity into account. When we say 2 positive real zeros, we could have 2 distinct positive real zeros, each with multiplicity 1, or we could have 1 positive real zero of multiplicity 2. 1 distinct positive real zero of multiplicity 2. Or it's possible here that we could have no positive real zeros. For example, consider y equals x squared plus 1 in blue here. This thing had no x-intercepts whatsoever. It has no real zeros whatsoever. Now, Descartes' rule of signs doesn't say which number it is, but like with the number of possible numbers of turning points, right? With the possible numbers of turning points, we list the possibilities. There could be 2 positive real zeros or no positive real zeros. Now, what about the possible number of negative real zeros? Well, like with even and odd functions, what do we do? When we studied even and odd functions, what did we study? We studied f of what? The opposite of x. And this is to find the possible number of negative real zeros. So consider f of opposite x. Every time you see an x in the rule for f of x, replace or substitute with the opposite of x in parentheses. So we get this, and we simplify. We get negative 4x cubed minus 5x squared plus 7x plus 2. This time, we have only 1 sign flip or sign variation from here to here. So what are the possible number of negative real zeros of f? The possible number of negative real zeros of f could be 1, the number of sign flips we get here. 1 is the number of sign flips or variations we get here. Okay. It could be 1, or we can't go to negative 1. So actually, Descartes' rule of signs is very informative here. We know that we have to have exactly 1 distinct negative real zero, and its multiplicity must be 1. Well, look at our red graph over here, right? It was the -1 over here. -1 was the only negative real zero for the function, and it has multiplicity 1. Notice the cut here. Now bear in mind, what if we had gotten something like 4 variations in sign? Then, like the rule over here, we take that and we keep counting down by 2s, and we stop before we hit negative numbers. So if we had had 4 variations in sign, then we would have counted down to 2, and then to 0, and we would stop there. So if f of opposite x ended up with 4 sign flips or variations, then we could have had 4, 2, or 0 negative real zeros. Again, a double 0 would count twice, a triple 0 would count 3 times, and so forth. So this may be helpful in conjunction with the rational zero test or rational roots theorem, for example. And again, sometimes Descartes' rule of signs will say that you have exactly 1 or exactly 0 positive or negative real zeros. Sometimes we get lucky and we get strong information like this. Okay. Now, part I on upper and lower bound rules, I'm not going to hold you responsible for this, but it is in my notes, so you can skim it over. Basically, you can use synthetic division to show that the real zeros of our polynomial must lie in some closed interval. And you put these numbers in the dunk tank, and you analyze the numbers in the third row. But that's an optional portion.
By the way, I lied or I forgot. There's one more video, but something that you'll appreciate, okay? We're going to use the factor theorem, and you're going to be able to factor cuties without having to guess. So this next video is basically optional, but I think you'll appreciate it, and you can finally show off to your Algebra 1 teacher. I want to show you this.
Hi, everyone. Here's a bonus topic. How do you factor cuties, quadratic trinomials, without guessing? That's something that you may have wanted to know back in your Algebra 1 class. Well, remember our old friend here. 4x cubed minus 5x squared minus 7x plus 2. In fact, we were able to factor that over z, the set of integers. Now, we used the rational zero test or rational roots theorem to find that 2 was a rational zero. So by the factor theorem, x minus 2 is a factor, and we could do synthetic division. We got this, that this equaled the factor x minus 2 times this quotient we got when we divided this by this. This QT was 4x squared plus 3x minus 1. And actually, a lot of students would have gotten stuck there. How do we factor that thing? How do we factor that? If you hate guessing, there's a way to do it without guessing. Because some students may not want to stare at this and try to figure it out from that. They might want to use what formula? Why don't we try using the QF, the quadratic formula? That should be able to help us. So let's apply the QF, the quadratic formula. Let's find the zeros first. They're potentially imaginary. In general, we're going to find the complex zeros. They could be imaginary. So when you find the zeros using the quadratic formula, you get 1/4 and -1, which means that by the factor theorem, x minus 1/4 will be one factor, and x plus 1 will be the other factor. Again, 1/4 is a 0, so x minus 1/4 better be a factor. -1 is a 0, so x plus 1 better be a factor. But now, don't forget, we have to rescale this so that we get the appropriate leading term here. The leading term here is not just x squared, it's 4x squared. You need the leading coefficient. This is like Lft form. It is Lft form. As it stands, this is Lft form. But wait, let's say we want to factor this over the integers. What if we want to factor this polynomial over z, the set of integers? here's what we could do. We don't like the negative 1/4 because it's not an integer, but what could we do? We could take the 4 out here, the leading coefficient, and multiply it through this factor. We can distribute. And when we do that, what do we get? We get the factor 4x minus 1, which is a factor over the integers. So then we get that this QD factors as the factor 4x minus 1 times the factor x plus 1, or vice versa. Now, many people might say, well, wait a minute. I mean, if you found the zeros to begin with, do we care about the zeros? Well, sometimes we do. Sometimes we ultimately want the zeros or the x-intercepts. But what if we wanted the actual factorization? Because let's say we have to simplify a rational expression like this. You would want to factor this QD, see what happens, and lo and behold, x plus 1 is a factor of the bottom of this QD. So you'd have to simplify, and you get 1 over 4x minus 1. So sometimes you do want to factor a QD for factoring's sake, or for the sake of simplifying. Also, another point I want to make. Let's say that your zeros aren't as nice. Let's say you get imaginary zeros, for example. Well, then you should be able to at least factor over C. We know that at the outset, we should be able to factor this over C using Lft form. We should be able to do that. And if these turn out to be ugly imaginary numbers, we know we can at least factor over C, the set of complex numbers. We know we can do that at this point. And remember, if you get a pair of complex conjugates here, then the corresponding factors would be x minus one of the complex conjugates. You'll probably need grouping symbols, times the factor x minus the other complex conjugate. Again, you'll probably need grouping symbols. And we have here a pair of CCs, a pair of complex conjugates. So the quadratic formula can be helpful, in part because you do sometimes get difficult imaginary zeros, but even if you could factor this over the integers and get rational zeros, you get rational zeros exactly when a guy like this factors over the integers, then you could use the QF anyway, use the factor theorem, and then maybe bring in the leading coefficient appropriately in such a way that you get factors over Z, the integers. And you can do this. So if you ever run into your algebra teacher on the street, your algebra teacher gives you this. If you know the quadratic formula and you know these tricks, you can produce something like this. Bear in mind, if you have something like this, where if you have a 6 on the outside, and let's say x plus 1/2 over here, and x minus 1/3 over here, let's say you got negative 1/2 and positive 1/3 as your zeros, then you have to be a bit more creative. Then you can split the 6 as 2 times 3. The 2 goes through here, the 3 goes through here. But you can get factors over Z. So you can use the QF to factor Cuties. You don't have to guess. You just have to be a little clever sometimes.
All right. Factoring Cuties without guessing. That's a nice thing to know. All right. So that's that.
Hi, everyone.
Nope. No more hi, everyone. All right. So we've done through, or I've done through 2.5. That's a big section. Lots of homework from there. All right. We're going to finish up chapter 2 with 2.6 and 2.7 on Thursday. All right. I'll take questions at this point. I'll take questions. Okay. Thank you all. Yes, that was a lot of material today, right? A lot of material, and just one video in there, right? So any questions? I'm still recording. I'm going to stop the recording soon. 3, 2, 1.